Hello, this is my English speaking practice, and I'm working on coding programs. But today I'm going to deep dive into built-in types like ref cell and RC types. Yeah. So yeah, this is what I left off yesterday. Yeah, so um, I solved this problem with binary tree, and in order to define the binary tree, we needed to use these types, but I don't understand what it is. So today I'm going to deep dive into these definitions like RC and ref cells, and also why this is needed. Right. So, in my current understanding, in the Rust, um, the type definition should decide its size at the compile time. So, um, basically, if I define like like this and like this. Yeah, we cannot define like this because recursive type tree node 2 has infinite size. Recursive without indirection. Insert some indirection to break the cycle. A type that is composed of other types. Structures comes in three flavors: structs with named fields, tuple structs, int structs. Yeah. So these types are called indirection, and yeah, we need to avoid the infinite loop, infinite size. Yes. So the compiler wants to define the size of the structure, but yeah, if the definition contains the recursive definition, yeah, the compiler cannot find out what size it is, so the compiler is picky, right? That's why we needed to introduce these types. But yeah, so this is my current understanding, but I'm not understand where. So for first RC, I'm not sure what does the RC stands for, but maybe it is reference counter. A reference counter, a single-threaded reference counting pointer. RC stands for reference counted. And so it has pointer, and I don't know what it is, but zero size type used to mark things that act like they own a T. but I think this is not important right now. Pointer and arrow A. Reference counted. And ref cell, a mutable memory location with dynamically checked borrow rules. Stores the location of the earliest current active borrow. This gets updated whenever we go from having 0 borrows to having a single borrow. When a borrow occurs, this gets included in generated borrow error, borrow mute error. So, so I think in order to avoid the recursive definition, the thing is to use the pointer. So I think I think it's enough to use only RC for just avoiding infinite loop. So I mean RC. Yeah. So we can do like this. But this is necessary. Why? RC is just single-threaded reference counting pointer, so it has a pointer, and so let me see the method. I think pointer RC new. I want to understand. I want to understand. You're on the right track. RCT is a heap allocated pointer with reference counting, which gives you shared ownership and also breaks recursive type sizing issues because RC is a pointer, its size is known. But there are two separate reasons people use RC left cell T in tree structures. Recursive type sizing. A struct cannot contain itself directly because its size be infinite. You need indirection. And box T or RCT, both are pointers, make the size finite. RC is chosen when multiple owners are needed. Multiple owners needed. Interior mutability. RCT gives shared ownership but only shared immutable access. To mutate through RC, you wrap the inner value in left cell T. Left cell enforces borrowing rules at runtime, not compile time. That's why you see RC left cell T in mutable tree graphs. So if you only need one owner, box is enough, no RC. If you need share ownership but no mutation, RCT is fine. If you need share ownership and mutation, RC left cell T. If you want, show me the exact use you were curious about, and I can tell you which pointer type is most idiomatic. Okay, so yeah, so one owner or multiple owner. Let me see. Multiple owner. Multiple owner. One owner. Multiple. What do you mean? If you also need to mutate, what do you mean? Share has two owners. Let me see. Yay, 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 yay. So in this case, the tree node, left and right, have to, yeah, left and right. But the node is always, node has always one parent, so I'm not sure because here is a base case, so the leaf node is given birth here, right? And return here, and borrow happens. Let me ask. I didn't. Yes, in your current tree, there is only a single owner. The num-array root owns the whole tree. Nothing is shared nodes, so RC isn't giving you any benefit. You can switch to box tree node. What changes conceptually? Ownerships become a single owner. A mutation should use mute and plain reference instead of left cell. So you'd end up with update takes mute cell and recursive helpers takes. Really? I didn't thinking of left cell. Keep only if you actually need sharing ownership or to mutate through shared references. Here you don't. Here you don't. If you want, I can refactor the file to box and show the full code. Wait. I haven't thinking of left cell. But the mutation happens here. Update and maybe here. And here, right? So borrow mute function mutably borrows and the wrapped value, and the borrows lasts until the returned ref mute or all ref mute derived from it exists. So the value cannot be borrowed while this borrow is active. Yeah, makes sense. Panics if the value is currently borrowed. You can use mute reference only if you have exclusive access to the node. In your current design, you call update on self, so you only have shared access to root. Rust won't let you mutate through a shared reference unless you use refcell. Interior mutability. Why refcell shows up. Shared ownerships. I see. I see. Often used with RC because there are yeah, refcell is usually paired with RC when you need shared ownership and mutation. If you don't need shared ownership, prefer box mute for simpler compile time checked mutability. to use box3 node and ampersand mut instead of rc left cell t. The tree is now single owner and mutation happens via ampersand mut self with compile time bro checking. If you want, I can add a couple of quick tests to confirm update and behavior. Okay, let's see. Tree node doesn't change. The definition are changed. The box is most foundational pointer type. Pointer type that uniquely owns a heap allocation of type T. So if you use box type, yeah, the data is the memory is allocated. The heap memory is allocated and the data is stored on it. And the box has its pointer internally, I think. Box. New box. Where is the there are no fields. The box structure must be kept in sync with pointer type. Anyway, as left. Great. And I want some refactoring. Yep. Root is yep. Root. And index is self root. Consider mutably borrowing here. Yep. So it's like this. Yes. And we don't need to check about like this, and left and right, and also it's like this, and maybe we borrow as mutable. Cannot borrow through as mutable as it is. I see. Left and right. Yes. It's okay. And build tree is fine. Update tree. Query tree is also fine. Let me see how it goes. Yeah, great. So let's wrap it up. But I want to understand. Shared child node. Two parents point to the same node. Okay. So yeah, shared pointer, and the node refer to the pointer, same pointer, and borrow mute is called here. Why box can't do this? Box is single ownership. A value can only have one owner. So at this point we cannot compile it, I think, if I use box here, right? So if you try to attach the same box node to two parents, you'd have to move it twice, which is illegal. You'd end up duplicating the node instead of sharing it. I see. And RC multiple orders, and you need a mutation while holding. Here I can show the exact form where you'd get trying to share. borrow mute. Borrow mute. Borrow mute. Borrow mute. Borrow mute. Borrow mute. Returns a left mute guard, and the mute borrow lasts until that guard is dropped. That's usually the end of its scope, not just a line. Ah, I see. A more complicated example showing nested borrows explicit scope control and why you sometimes need to drop guards. Bump left, then right. Root, borrow, mute. So, mutable borrow root to get left child. Clone RC to keep child outside this borrow. Left opt. If there is left opt, mutate left independently. Now we can borrow root again. The mutable borrow lasts as long as the left mute guard lives. You often create a block scope to drop the guard early. Drop the guard. Root mute dropped here. Makes sense. And in order to get the left child, clone RC to keep child outside this borrow. So it's like take the left child from the root node, right? But the root mute borrow drops here. And get it and borrow. Borrow mute. no matter how many, no matter how many. Okay. So, borrowing rules are the same, but the difference is it's active at runtime. exactly one borrow means at the time. Okay. Overlap is not okay. It's panics. So borrow mute is exclusive, just like mute. Ah, I see. I see. I'm not sure why. Really? You only have shared reference and the compiler can't prove when you'll borrow or how many owners exist at runtime. If there exists specifically for cases where you have shared ownership but still need mutation, the aliasing is only knowable at runtime. So the compiler pants the check to runtime and borrow mute to dynamic checks instead. If you restructure to use mute single on an RC, then it is enforced as compiler time. Really? So, for example, borrow mute continues until here. So at this line, this borrow will be failed. But the compiler isn't picky. Okay. But in my Yeah. Hmm. I think it can detect. Hmm. Hmm. Because the compiler only enforces borrow rules for static borrows here. Hmm. Borrow mute returns a guard from left cell and the aliasing happens through shared ownership. Can't see or track how many aliases exist at runtime, so it can't prove the rule statistically. Left cell is specifically designed to defer those checks to runtime. That's why the compiler allows it, and the panic happens only when the borrow rules are actually violated at runtime. Yeah. So, 原理的には、原理的には、I understand. It is implemented as it is. Theory. Theoretically, yes, but not in rasters. To check this at compile time, you'd need a type system that can track aliasing through RC and enforce uniqueness across all owners, something like linear affine types or different ownership model. With shared ownership, the compiler cannot know at compile time how many aliases exist or when borrows overlaps, so it's not decidable in general. So possible in more advanced type system, but just choose left cell as a practical explicit runtime checks. Escape hatch instead of trying to make all such cases compile time verifiable. So They are different. Compare time borrows, the compare checks shared ownership. It doesn't borrow at all. Left cell. I made a mistake about this. Left cell provides runtime borrows and it checks rules. So it's just highs. Oh, I want to know about this. The comparer can't know how many owners point to the same values or where they are at compare time. Is as the comparer sees all aliases in the current scope and can enforce the rule. With RC, you can clone it, store it anywhere, pass it across function, and the compiler loses track of who else might be hold that pointer to the same location. So now there are 3 owners of the same allocation. The compiler doesn't know how many clones exist in general or when they get dropped. That's what aliasing is here. Multiple pointers to the same data. So the compiler can't safely allow ampersand mute access through RC because it can prove uniqueness. That's why you need RC left cell to do dynamic checks. In contrast, box T has exactly 1 owner, so the compiler can prove uniqueness and allow ampersand mute. If you want, I can show how RC's clone plus runtime borrowing interact with the congruent example of the Parix. So the pointer are cloned. So the left cell is will be cloned many times. So the compiler cannot track it. I see. A mutable reference cannot be cloned or copied. It's exclusive by design. You can copy T, but min is non-copy, so you can't create another pointer to the same data. If you want pointer like clones, that's RC, but then you lose compare time mutability guarantees and inner left cell or mutations. I see. Yeah. That if the original entity is clonable, it might be aliased many times, and it get impossible to track, to be tracked. So cannot prove it and apply. If something is clonable into multiple aliases like arrays, the compiler cannot prove uniqueness, so it can't enforce ampersand mutable rules statically. That's why you need runtime checks in those cases. So the difference is the original entity, original data is clonable or not. If it's clonable, yeah, and if you want to, share, if you want to share it, yeah, if you want to share it, if you want to share it, it means the data should be clonable, or clonable, but it's not clone, it's a clone of pointer. That's confusing. So there is only one entity, and if you want to share it, you have to use shared pointer, and for that the RC, reference countered type, is used. And in that case the compiler cannot prove uniqueness, so it can't enforce borrow rules statically. So so we use the left cell type, and the borrow rule are applied at the runtime, because it's impossible to enforce the borrow rules at the compile time. And so the RC and the ref cell are used at the same time. Because we want to use shared pointer. But I'm confused. Why? separated. Shared ownership, no mutation. Shared read-only data. Shared read-only data. Shared read-only data. Ampersand is enough only when a single owner controls the lifetime and all borrows fit within the scope. You need RC for shared read-only data. Oh, really? You want multiple owners with independent lifetimes. You need to return shared data from a function without trying it to borrow the lifetime. You want clone handles cheaply and keep the data. Borrowed view with a lifetime constraint. There are difficult concepts. There are a lot of difficult concepts in Rust. So I need to learn about the difference between borrowed view with a lifetime constraint, owned shared handle with Here's a simple example where ampersand t is not enough because the owners need independent lifetimes to structure both on the same data. There are config and service A and B, and it uses RC. Clone. CFG lives as long as both services. If you try the Ampersand config, you'd need config to live somewhere outside of both services to manage lifetimes manually. RC makes them independent owners with automatic lifetime management. If you want a constraint contrasting I've seen it. I've seen this. This works because CFG lives in main and both services borrow it. But you can't return services that outlive CFG, and you can't store them in a place that requires static without extra lifetime proofing. That's when RC becomes useful. Yes, constraint. Creating CFG and周期を持たず元の値の需要に必ず依存します。参照先が生きている範囲内でしか使えない。共有所有権。参照カウントで寿命を管理するから複数の所有者が独立して生きられる。なるほど。独立して保持したいので RC が向いていますと。コンフィグの寿命が常に外側に固定されるので柔軟性が落ちますと。外側に固定されるというのはあれか。外側っていうのはここがやな。ここ側にされるからまあそうですね。所有権。In Japanese, I can understand, but so I want to read the English sentence again. Here's a sample example, and not enough because the owners need independent lifetimes to select both on the same data. If you tried Amazon config, you'd need the config to live somewhere outside both services and to manage lifetimes manually. You need the config to live somewhere outside both. RC makes them independent owners with automatic lifetime management. If you want constructing example, this works because CFG lives in main and both services for it. But you can't return services that outlive CFG, and you can't store them in a place that requires static lifetime and without extra lifetime pumping. That's when RC becomes useful. So I understand the importance of reference counter. It's for managing lifetimes. Yeah, so as long as there is a reference counter, the T should live. So yeah, so the lifetime management becomes simple, right? For this, it's just borrow. It's just a borrow. So mm, yeah. So the the owner doesn't change because it's just a borrow. So the lifetime depends on the original scope, depends on the owner, right? So hmm, if you want to use t if you want to use t as how do I say if you want to treat t as your own, use rc instead of borrowing it. If you want ownership of t, use rc rather than borrow. When you need to own t, use rc instead of borrowing. If t should be owned, not borrowed, use rc. And back to the difference between RC and ref cell. So ref cell is used for mutation. Interior mutability. multiple owners. There are common motivations to avoid mutable self-reference. If several objects need to hold the same data, API convenience. You want two methods callable on. Makes sense. Shared immutability within patterns like memoization within. I see. So for API convenience, the caller doesn't need mutable self-reference. Right. I'm getting it. Shared immutability with patterns like memoization. I don't quite get this, but it's okay. It's okay. So let's call it a day. It was a good study. I learned about RC and RefCell and Box, right? Box is just a pointer type, and the data is stored on the heap area. And when you define the structure like that contains recursive structure, you need to use pointer type like box or RC, because when compile time, the compiler should find out the how what size the structure is. So in order to avoid the cyclic definition, we needed to use pointer type. So we use box type here in this case. And there is one more pointer type I learned today, that is RC, that stands for reference counted. And this is for shared pointer. So if you want share something, you can use RC, and thanks to this, you don't need to manage the lifetime management, right? So yeah. So basically, this pointer type is used for sharing something to multiple owners, right? So maybe you will use clone function, which clones a pointer, right? And left cell is often used with RC type because left cell manages the borrow rule at the runtime, right? But yeah, this is used for mutability, right? Mutability. And so in this example, we compare box and simple type and RC and left cell and T. Yeah. So in this case, there is one owner. So so in this case, the compiler can prove the uniqueness. So we don't need to use left cell and borrow checking at the runtime. We just use box type and MUT keyword like this. So the compiler assure or prove the ownership. There is always only one ownership, right? If there are multiple ownership, you need to use borrow mute function to update update internal value of left cell. And this function, borrow, mute, and borrow function, might cause panics because it checks the borrow rules at the runtime. So you need to care about it. And yeah. That's it. Oh.